Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but you know, I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah.
Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everybody. Hope you're all doing well. Um, hey, everyone. Welcome to the Ask Us Anything About Electrochemistry podcast. My name is Dr. Alex Paroff. Normally, my colleague, Dr. Neil Spinner, is with me, but he is out on vacation this week. And so I guess I'm just running the show today. Welcome, and thank you all for attending. For those of you who do not know, Pine Research, about once a week on Fridays, we try to host an Ask Us Anything About Electrochemistry podcast. This is a time where you can literally ask us anything. We'll try our best to answer your questions, but we know that electrochemistry is a very complicated and complex topic. A lot of people sometimes struggle or have issues just trying to understand some of the concepts of electrochemistry, or don't know how to troubleshoot a specific problem. And we get a lot of questions from YouTube and email and telephone and webinars, all kinds of things. And sometimes those are not always the best, I don't want to say, venues for trying to solve or answer your questions. So that's why we have this live stream. For those of you who are on, please give me an audio check. Can you hear me? I hope that this is making sense. I'm going to keep an eye on the chat in case people are humming, but please let me know if you can hear me. I think everything is set up correctly. Normally, Neil does a little bit of this checking for me. So the format of the Ask Us Anything About Electrochemistry is as follows. We usually do this for about 2 hours. We'll just be on live. Type your questions into the chat, and we'll try to get to them as soon as possible. If by chance you're unable to make it to the live stream, sometimes people will ask us questions in advance, and we'll try our best to answer those questions during the live stream if we can. Of course, if you are here during the live stream and you ask a question, we're going to try to get to your question as soon as possible. Now, we also tend to give priority to our tier 1 and tier 2 members if they ask a question first. Sorry, I'm eating a mint. It's very delicious. And we'll tend to give them some priority. But this is also one of the first times we are trying an instance where you can actually join us on the live stream. So we're using Restream right now. You'll be able to join us in the Restream channel to actually talk to us instead of just chatting through typing on YouTube. You can actually talk to us one-on-one, and you'll have a chance to share your data. You can actually share your screen. You can share a cyclic voltammogram or an EIS plot, and we can try to answer some of your questions and actually talk you through the process. So this is for tier 2 members. And if you're a tier 2 member, I just put a post about maybe 15-20 minutes ago, a post with the login, basically a link to this live stream. So if you have it, you can put that into your browser, and it should allow you to join this Restream as a guest. And we're testing this out for the first time, so we'll see how that goes. Lastly, a couple things just to note is I'm going to apologize in advance if I mispronounce anybody's name. I'm sorry. And I know some of the names on YouTube are just kind of numbers and letters or Pokemon or stuff like that. So again, apologies in advance. And then there are no stupid questions in electrochemistry. This is a safe space where you can ask us whatever you want, and we're going to try our best to help answer your question, or at least provide you with some ways to kind of move forward if we cannot provide the answer, where you can go to find answers. All right. So I'm gonna look through and see if I can get some questions. I have some pre-canned questions from other people who've asked questions. All right. It looks like we have Sadaf Sadiq. as a question. Let's pull that up. Sadaf says, hi, this question I already asked you earlier. Being newly to in electrochemistry, I often get confused about redox potentials. I'm doing research on supercapacitors, and the electrolyte is sulfuric acid. All right, and so I guess uh, if you want to form that in the form of a question, it looks like you want us to learn a little bit or talk a little bit about what are redox potentials, Sadaf. I think that's what you're asking. So hopefully, what I can talk to you about now is just kind of what are redox potentials, and it's a good question because redox potentials are actually a little confusing and complicated. If you come from a chemistry background, redox potentials are not used very often. More often than not, a redox, like you're usually using things like kilojoules per mole. You're using things like just concentration. You're using energy. Maybe you're using wave numbers, wavelength, um, centimeters squared. Joules tends to be the unit of energy that we use to describe things. Electrochemistry is one of the few parts of chemistry that discusses a quote redox potential. But the redox potential also is related to many things. And I think stuff actually gives me a little bit more information about the question. So reference electrode is silver chloride, activated carbon as the counter electrode, and the active material is nickel oxide. I'm running cyclic voltammetry. I think that's between 0.2 to negative 0.6. I'm seeing small redox peaks. I am confused. Are these peaks for the nickel redox centers? Okay, so that's a great question. Fantastic question. So I'm going to leave this up. Let's talk about it. So you say that you can see small peaks, and you're working on an activated. I said activate carbon as the counter electrode. I might ask a little bit more what the working electrode is. Is the working electrode also carbon? And nickel oxide is it says it's your active material. So it looks like you're looking at the active material. So there's a lot of stuff. I hate using the word to unpack, but perhaps I can provide you with a little bit of information. So what I'm going to try to do is I'm going to share my screen. I'm going to share kind of the window. Let's see. Oh, gotta make sure that this is open. All right. So I'm going to share my PowerPoint just so that you all can at least see. And let me maximize this and just kind of maximize. Minimize my face. Is that here we go? Let's see. Work on a couple details. Okay. All right. There we go. So you can see me, and you can see the PowerPoint. All right. So before I begin, actually, I do want to address one thing, which is I didn't actually mention anything about redox potential. So it's important to understand in chemistry, the redox potential has to do with the thermodynamic driving force for a reaction to occur. That's really what it's saying. It says that when you have some kind of redox reaction and there's a potential associated with it, that potential is indicative of the thermodynamic driving force to get the reaction to occur. And there are relationships between the Gibbs free energy, delta G, and the E naught, so the standard or the formal potential. And it's interesting because delta G is an energy, Gibbs free energy is an energy, and E naught is a potential, which is different. But they're related. When we have, say, a negative delta G, we say that a reaction or that process is spontaneous. And when we have an E naught, a negative delta G tends to correspond to a positive E naught. And we would also say that that process is thermodynamically favorable. Well, what does that mean? Because normally we hook up things to potentiostats and stuff like that. Well, that process is still happening. So things like oxidation. So I should also clarify that potentials, even though there's a thermodynamic relationship, there's the delta G related to E naught. E naught only refers to reactions where there's an electron transfer. So that's one of the main things. The potential always refers to an electron transfer process. Okay, so we're talking about the thermodynamics of the driving force for something to happen. Now, sometimes those potentials are positive. All right, so if it's a positive potential, that means that process kind of naturally happens. It has a negative delta G. It's spontaneous. So, as an example, silver oxidation is an electrochemical process. The oxidation of silver to silver oxide has a positive E naught. Same thing with copper. And we know this because silver tarnishes. Silver, if just left in the atmosphere, will undergo an electron transfer. It'll oxidize just naturally. Rust, iron oxidation, is a naturally occurring process. So sometimes we tend to not think about like what do these potentials mean, and does it always mean I'm applying some force to get something to happen? No, those things can also just happen naturally. Now, to talk about your issue with kind of the reference electrode and silver chloride and activated carbon, I'm going to go back to the PowerPoint and try to describe this a little bit more. Hopefully, provide you with um, some information, maybe something to helpful. So, one thing to note about potentials is that they are all relative. Potential is a relative quantity. Delta G is kind of an absolute quantity, but potentials are relative. And so, what we do when we're doing measurements is we have a reference electrode which acts as a stable point to with which we apply a potential with respect to. So, silver. So you can kind of think of you have this kind of potential energy level, sort of say, not energy level, but this potential scale. And somewhere in the middle, there is this SHE, what we kind of define as the 0 point. And it's defined by a reaction, the thermodynamics of this reaction. And that's something like 2H plus. I'm going to write this because it's going to look weird if I type it out. But if I just write this as like, say, 2H plus plus 2 minus, and that's an equilibrium, kind of a dynamic equilibrium with, that didn't turn out right, but I think you get the picture, H2, and that's usually a gas. Okay. So let me delete that for clarity. So this reaction is defined of having an E equal to 0. That's just what we've defined it as, which to a degree is somewhat arbitrary, but that's what we've done to define it. And so when we go back to here, when we have something like silver plus or silver chloride, AgAgCl, the potential of AgAgCl, the silver chloride reference electrode, is relative to this process. This is something like, I believe, if memory serves, it's either plus or minus, and correct, I'm sorry if I got this wrong. It's something along the lines of 200 millivolts, 190 like 6 or something. So the potential of this reaction with respect to this reaction is 200 millivolts. And these potentials, in many ways, are absolute quantities. Like, it's based on the chemistry of the redox reaction. This redox reaction is governed by this E naught. And there's a redox reaction here. If I remember correctly, you'll have something like, let's see, if it's a reduction, it's based on silver chloride. So if I have something like silver, I'm going to write the complete reaction. So you may have something like silver plus 1 electron, and actually you start with, silver chloride plus 1, actually it's minus 1 electron here, so it's products of reactants, so maybe 1 over, I'm sure I'll get this, if I remember correctly. Silver chloride, and then you generally, when you split this, you have Ag plus, so actually this is plus 1 electron, 1 electron, E minus, and that gives you silver metal plus chloride minus anion. And this is the redox reaction that governs the potential of this silver chloride. And let me just make sure, I want to make sure I'm not losing people. Okay, good. I don't think I've lost anybody so far, or have any new questions. So when you pick this potential, when you pick this kind of this as your silver chloride system, you are when you're doing a reaction, when you're sweeping the potential between, I think it had let's see, it was 0.2 to negative 0.6. That means, like, from this point, if this point is 0, you're going from 0.2 on this side all the way to negative 0.6 on the other side. So at this 200 millivolts of silver chloride, you start 0.2 volts positive of the silver chloride redox potential. You're sweeping negatively to negative 0.6 with respect to the silver chloride redox potential. And you're observing nickel oxide peaks, or what you appear or think are these nickel oxide redox features. And the idea is, and the question that you have actually has to do with, are these peaks for the nickel oxide redoxes, or redox species? And really, the only way to determine this, Sadaf, is that you need to do the experiment with and without the nickel oxide. And if you do the experiment without nickel oxide and you don't see those redox peaks, then it's most likely the case that those redox peaks are associated with nickel oxide, and that the oxidation reduction process that's happening of your nickel oxide is within that potential window from 0.2 with respect to silver chloride, and negative 0.6 or negative 0.6 also with respect to silver chloride. So whatever that redox feature is happening there. Now, is it due to nickel? Could it be due to oxygen? Are you reducing oxygen? Oxygen is oxidized. That's also another thing that could be happening. So there are a couple variables that that you may need to think about and consider. But I think that Sadaf is probably the easiest way to determine whether or not what those small redox features are, because you've applied a potential that's thermodynamically sufficiently oxidizing or reducing. I don't know the direction of the redox peaks, but it's oxidizing or reducing enough to create an electron transfer, most likely with that nickel species. So, Sadaf, I hope that was helpful. And let me know if you have any further questions. I'll try to address them or add additional clarification. Okay, Sahid, hello. Please, what could be the reason of an LSV, linear sweep voltammetry, of hydrogen evolution or hydrogen evolution reaction displaying zero current at zero potential? I am not starting from zero at the current axis. What could be done to address this? This is a great question, Sahid. Very, very good question. So let's, I'm going to pull this back up. I'm going to actually get rid of this. So let me just use, I'm going to use the lasso tool here and kind of delete everything. Oh, that's actually something I have to just highlight and delete. Okay. So let me just make sure I have the question correct. Right. So what you're seeing is the following. You are at, so this is, let's just say this is 0 volts. Or sorry, this is 0 current. This is current. This is voltage. And let's just say this is 0 volts. Now, normally you would expect that there's an intersect that when you start your experiment, it's going to be here. But in reality, maybe your experiment is starting here as you sweep your reaction. And let's say if you're doing HER, it actually would probably go, depending on where you're at. If you're doing HER, I think you're probably looking maybe something like this, or maybe you're looking at something like this. But the question in turn is, why is it that at 0 volts you're not getting 0 current? And this is a very, very good question. And the reason, in short, why you might not be getting 0 current at 0 volts is because 0 volts is always with respect to something, right? So it's 0 volts with respect to your reference electrode or respect to OCP or something like that. Most likely it's your reference electrode. Well, just because something is 0 volts doesn't necessarily mean that no current is flowing. In fact, it may be a positive or a negative voltage with respect to another reference electrode. That's completely possible. Think about copper, for example. So copper electrodes, so let's just go. So copper, naturally, if I just have a bit of copper, I'm not applying a voltage to it. But copper will oxidize. It'll lose an electron and it'll form some kind of copper oxide. I don't know if this is, copper oxide, something like that. Maybe this is 2 electrons. Go from neutral to 2. Copper can undergo a lot. This happens normally at no applied potential. You could start your experiment, hold it at 0 volts, and you would actually have an oxidizing current at this working electrode. So this is to say that 0 voltage does not mean the point where there's 0 current, or more specifically, the voltage at 0 charge. There can still be charge on your electrode surface, even if the voltage is 0. And hopefully, by kind of thinking about the thermodynamics, as I talked about earlier, if you think a little bit about the thermodynamics, naturally something might be happening at your electrode surface. So now you're doing HER, right? But that doesn't tell me anything about, say, what your working electrode material is. It might be, or what your electrolyte is, or what your reference is, or anything like that. But generally speaking, this is kind of like what could be happening. There's a reaction naturally occurring. And I would also ask, like, what is 0 current? 0 current may be nanoamps. Stuff might be happening at nanoamps. So there may be a little bit more clarification, but hopefully this gives you a few reasons, Sahid, why you're actually getting a non-zero current at 0 volts. Okay. Hopefully that's helpful. Please let me know if you require any further explanation. All right, so let's take a look. Next question. And again, for any of you who are watching, if you have questions, please let me know. If you're a tier 2 member, you can, if you go to the community post, you can also, you can actually join. We're trying this new where you'll actually have the option to join us, and then you can share your screen to share some of the data and information if you want to ask questions. Okay. Yeah. I want to do CCD with 3 electrode system, but I can't fix the parameters. Can you please discuss the parameters which have to input while doing this test? Yeah, I'm not sure I know what CCD is. Can you tell me? And then I will. Sometimes there there are a lot of acronyms in electrochemistry, and sometimes I just don't know. What they what they are. What kind of experiment is it like a is this a discharge experiment for like a battery or something like that? Neil, of course, is also the battery expert, so he may I may or may not know exactly the right answers because I haven't worked with batteries. So Bia, if you give me a little more clarification, I should be able to help you or provide you with some additional support. All right, so what I'm going to do very quickly is I just want to clean up my PowerPoint. And while we wait for some upcoming questions to come, or some clarification from some previous questions, there was a few questions that we get ahead of time that I'm hoping to at least address some of them. These are from a member of ours named Tarek, and let's see if I can go through some of them. So this may be a little hard to read, but hopefully hopefully you can see them as I type them out. Well, actually, let's see, did I get oh wait, okay. Before I go to this, I want to get to Bia's question. Sorry, Tarek. I will get to your question as uh as Bia just said. Cyclic charge discharge. This is cyclic charge discharge. Okay, so this is again. I want to do cyclic charge discharge with a 3 electron, but I can't fix the parameters. Can you please discuss the parameters, which is the input testing? Okay, so this I assume is for a battery, and I know Neil's kind of the battery expert, but my understanding is that you're probably going to use galvanostatic mode, I believe. Um, you may be doing this in potentiostatic mode, and I think it will depend, or it's like just charge discharge with a 3 electrode system. So, Bia, can you also confirm, is this a battery, or is this like a regular 3 electrode system with like an aqueous solution? You have a working counter and reference electrode, because I believe you mentioned previously that you might be doing battery work in a 3 electrode, in the traditional 3 electrode system. But basically, in short, with kind of what are the parameters, um, let's see, I can't fix the parameters, discuss the parameters which you have to input. So he's talking about also in the potentiostat, what parameters do you put? Well, you'd want to set, probably, my guess is, let's see. Yes, so it was confirming, yes, battery, supercapacitor, but it's a 3 electrode system, which at least in this case means that you have a battery system. Okay, so it's just like you know what your reference electrode is. I'm not 100% sure, but generally speaking, I think you're probably you're charging the battery with a constant current. So probably one of the parameters that you're going to fix is the current. You're going to want to fix the rate at with which your battery is charging and then discharging. So you're going to probably have a positive current as well as a negative current for the charge and the discharge, depending on anode and cathode. Anode and cathode of your battery. And I think what you would probably do is you would want to set. My opinion is you'd probably want to set a very low current. Like, you don't want to charge the battery very, very quickly. You probably are going to want to charge it slower, because if you don't know what the potential is that's supposed to go up to, then you have a strong chance of damaging the battery. So a parameter that's usually used is like there's currents, like the rate at with which you're charging and discharging, and you probably have a cutoff potential, which is you don't want the current, you don't want the potential, like you're doing chronopotentiometry basically. You don't want the potential to go above a certain amount, so you create a cutoff voltage. So it'll charge. The current is staying the same. The potential is shifting, and then it reaches its cutoff voltage, and then it switches back and goes down the other direction. Let me see. Bia has a little bit more clarification. I want to do this CCD for anode of battery, but just not the whole cell, just the anode. That is the working electrode, then reference and counter. Oh, okay. And I guess in that case, you may be treating this as like a very, I would say, traditional 3 electrode system. So I don't even have to worry about all the weird stuff that can happen with batteries and possibly blowing them up, because that's always a risk. With charging and discharging, I think you would still probably want to go with galvanostatic, because galvanostatic is the way you're going to know that, like, oh, I have, quote, charged the battery, and then you've reached a certain potential. But it looks like you're only dealing with half of the reaction, because it's just the anode. Your cathode, being the counter electrode, can actually kind of just charge. I mean, you can, quote, charge indefinitely, sort of say. So I might suggest, you know, if you're sweeping back and forth, like cyclically charging and discharging, um, you'd want the number of sweeps. That's a parameter. You'd probably want either a potential that is within the electrolyte or based on the battery power. So I think like lithium, for example, has like almost 4 volts, I believe. Of course, it's in non-aqueous solvents. Otherwise, you'd be generating tons of hydrogen or oxygen. Um, but yeah, I think really like if you let one parameter go, like one parameter has to kind of be fixed, which is like, oh, I'm going to charge my, apply a current and then stop applying the current or apply current in the other direction. But then I think you're still going to want to have these cutoff potentials as a parameter where you don't want the system to go beyond a specific potential because it's going to destroy some other part of your electrode. If you're worried about the anode, maybe your anode can take a higher potential or higher voltage, but the electrolyte might dissolve or change in some or get destroyed, eaten up. So you don't want the potential to just rise indefinitely. You want it to go up to a certain point and then you want it to discharge. So Bia, I hope this is helpful. Um, so just kind of to reiterate, number of cycles is the parameter. The current that you want to select, which is the rate at with which the charging is occurring and the discharging. And then you want to cut off voltage that is sufficiently within the range of the redox molecule that you're looking at, but not so high that it's eating up the electrolyte. So that's the way I would think about it. That's the way I would approach it. Okay, we got a couple other questions. So that means I'll be looking at the Tarek's question later. So let's see. Um, Pranav, sir, I am doing research on electrochemical sensors, glassy carbon electrode modified with metal oxides. In cyclic voltammetry, if we got redox peaks in presence of particular analyte, how can we conform whether it corresponds to redox reaction of analyte or the metal oxide? Pranav, this is a very good question. Well, to do this, you would want to take a blank cyclic voltammogram of just your metal oxide, your glassy carbon electrode with the metal oxide, and just in your electrolyte solution, take a cyclic voltammogram within the potential window that you do it with the analyte. So you have your CV without any analyte, and then you have the CV with the analyte. So you add the analyte into it, you pipette it or drop it in, and then look at if there are differences, if there are peaks with the analyte presence, or peaks that are from the metal or that are from the metal oxide without the analyte. So this sounds like a situation where you just want to do a control experiment. Cyclic voltammetry without the analyte with the metal oxide. You may even do an experiment with just a glassy carbon disc without any metal oxide with the analyte, because this may also demonstrate that your analyte is interacting with the metal oxide. It will tell you if it's a homogeneous or a heterogeneous electroactive species. So, Pranav, I hope that was helpful. Please let me know if you have further questions or clarification. All right. Abe, I hope I got that right. Hello. I read that carbon paper can't be used on the anodic side of proton exchange membrane working electrode because it oxidizes easily. 2 volts, less than 1 pH. But it also mentions that carbon GDLs are used for proton exchange membrane fuel cells. Okay, so that's something that he read. And then carbon oxidizes at positive 0.207 volts per C via this reaction, the formation of carbon dioxide. Don't the proton exchange membrane fuel cells, PEM fuel cells, also operate at approximately 1 volt? Okay, so I think what what he's asking for. Let's see. So I guess the question is, how is this possible? How is this possible? So let's see. Carbon oxidizes. So I think to say that carbon oxidizes at plus 0.2 volts versus standard hydrogen electrode, the question is also, is that at pH less than 1? And I'm also somewhat on the fence that the carbon is completely turning into carbon dioxide. Um, that's at least just my initial look. I'm going to take a look at your other thing. It oxidizes easily. But also mentioned carbon used for fuel cells. I mean, carbon isn't disappearing into CO2 at the PEM fuel cell. Sometimes there may be thermodynamics, at least without knowing exactly the answer to this. You might say there's a lot of thermodynamics. You say thermodynamically, this is a very favorable process, but it doesn't happen, which means that it's probably a kinetic limitation why the carbon is not just oxidizing like crazy into CO2. Um, there's probably some reaction steps within this mechanism that are preventing it from happening. One thing that I'm looking at right now is you may have carbon and then you have water. That water's got to be split, right? That water's got to break apart and generate 4 protons, and you got to break some oxygen bonds there and have it form with carbon. I think there's a lot of kinetic steps that make it so that uh, this process of converting the carbon to carbon dioxide is not kinetically happening. But I haven't worked too much with some of these PEM fuel cells before. I also don't know, whether the PEM fuel cell is under acidic versus basic conditions. The nature of the reactions are also different. So in under acidic conditions, acidic conditions, this definitely is more favorable because you have a lot of hydronium. That the 4H plus is happening. But PEM fuel cells also operate at approximately 1 volt. Yeah, so I don't know if that's helpful or not, but it's also something I don't know. I don't know quite as much about. But I would at least just say that another thing is other stuff could be happening at the end on cathode. And it's not to say that there isn't some carbon oxidation processes that are not happening. A lot of stuff is happening at the surface. There's stuff that might be happening at the surface, maybe even forming a carbon oxide a carbon oxide layer on top of pure carbon graphite. So maybe that might be somewhat of an explanation. I see a few questions. I do want to. Pranav also asked a question related to kind of his initial question about doing cyclic voltammetry, which is how to solve stability issue in cyclic voltammetry. So this is not related to the previous question, but I'll hopefully be able to answer. So it depends what you mean by stability. Stability being, and maybe I can try to provide a little bit more information. And perhaps you can clarify what you mean, because when I think about stability, you have your voltage, you have your current, and then sometimes you may have like kind of noise on the cyclic voltammogram. Maybe it looks like this. I'm trying to intentionally create jagged lines here. So if this is the stability issue that you're kind of worried about, this kind of stability can also look like this, just like oh, you're getting lots of noise, kind of wobbling. Those are like oscillations. So there's many different types of what I would describe as like stability. But instability issues can be caused by a lot of things. The working electrode and the reference electrode in particular can cause stability issues. So your reference electrode is very important. There are stability filters in your potentiostat that also play a role. And so hopefully you can provide me with a little bit more information about what kind of stability problem you're running into. But whenever I think about stability, it usually has to do with noise, little bits of noise. So grounding configuration is very helpful, which is something I might talk about later. And then there's a stability filter setting in your potentiostat as well. So picking the right stability filter, which is also based on the scan rate of the cyclic voltammogram, those are other issues. So try doing some experiments at slower scan rates might be one way to do. All right, we have a question from Bebeto. Bebeto, I hope. Sir, I want to run a CV between 0.4 to negative 0.4 in PBS electrolyte with reference electrode silver chloride, counter electrode platinum to obtain redox peaks. The follow-up, since my working electrode is glassy carbon electrode modified with metal oxide quantum dots, is there any way to predict the redox peaks before actually running the CV? Probably not. I don't know what kind of quantum dots you have, what kind of metal oxide quantum dots. I mean, I know there's things like cadmium selenide, but that's not an oxide. That's a mixed metal alloy. I think it's relatively hard. A couple of things to keep in mind with the PBS electrolyte. It's an aqueous system. I think PBS is a buffer. You're going to have like a reasonable potential window in water that's between plus minus 1 volt approximately. Oh, sorry. Sorry. And what redox species or things that are going to happen on your quantum dot, I don't know if it's very, very well predicted, but I think it's best to run the CV and just kind of see what you get. There may be some inherent redox features due to the quantum dots, and maybe some of those things are predictable, especially if they've been published in the literature. But I don't think that there's too much you can do besides doing it. Like you need to either see it in the literature or just run the CV. And I think running the CV is probably the easiest thing to do. And getting some data and comparing it to what's been done in the literature is going to be very helpful, Babento, as you try to look at what could be happening. Of course, you're looking at let's see, you're looking at 0.4 to negative 0.4. You may actually not see very much at all if you don't know enough about your metal oxide quantum dots. So, the chemistry could be at some other place. There could be some redox species. Okay, let's looking forward. Gorab, is it necessary to run CV and GCD in the same potential window? Galvanostatic discharge. Probably. I'm going to say probably because your electrolyte system is what governs the potential window. It's not necessarily the electrochemical technique, but rather the materials that are being used. So the electrolyte, the electrodes, all of that, whether you're degassing the solution, all of those things are going to play a role in your potential window. But the technique itself that you use, that won't do quite as much. All right. So hopefully that was helpful. Please let me know if you need further. I think actually before I get to the album, let me see. I have an issue with my material during a rand galvanic discharge. A low current density, 1 amp per gram. During my discharge time, I got saturated before reaching the lower potential window value. Any physical reason? Oh, so if you've been running galvanostatic charge discharge, even running low current density, which I don't know, 1 amp per gram. I don't know. That sounds high, but I'm not a battery person. During discharging time, I got saturated before reaching the lower potential. Any physical reason? There probably is a physical reason, and I don't know the answer because I don't know enough about batteries, about what's happening in the quote degradation process. But I imagine if you've been cycling numerous times, then something's gonna something's going to give, or some part of it. I think there's a lot of people who actually study the degradation process of batteries. What happens as you charge and discharge them so many times, so often. So unfortunately, I don't know if I have an answer for why, what the physical reason is. If you're getting lower potentials each time, something's breaking apart. I think, because batteries are basically, battery potentials are usually very, very stable. It's just like the charge that they hold is indicative of kind of the breakdown of it, but the potential should be like the same because it's based on the redox potential of the thing moving back and forth, like lithium, right? Like lithium ion. That potential doesn't change. So the battery going to a lower potential than before, or not as high a potential as it used to, it's indicative of some other problems. Okay. Ugh. Sorry, very tired. I've been trying to consume less caffeine, just for, I don't know, health. Okay. Bia, one more question. You can always ask more questions if you want. I'm trying to do CV of PVDF plus silicon oxide nanofibers using a platinum electrode and trying to deposit the fibers on a platinum electrode as they are uh, as uh, as they are without making its slurry. But after testing, I think the peaks or reactions are only because of the platinum electrode. Could very well be the case. Can you suggest some method in which I won't have to damage the fiber's structure, as in making a slurry, and still contest them? So my thought to that would be, you might need to, if you're worried about platinum playing a role, which I think is it's a very legit concern. Platinum can do a lot of stuff. Try using carbon. And if you're using platinum as like a wire, then using something like a graphite rod. Of course, doing things like cyclic voltammetry experiments before and after, like, it's really good. Actually, a lot of the questions that people have been asking, um, a lot of the solutions are just take a cyclic voltammogram before and after. And it's very, very good practice to take a background blank electrolyte CV and then add the analyte in question afterwards and then see what you get. Is it going to look exactly the same in terms of like the background current or the areas where nothing's happening? Probably not. The double layer charging, that whole thing will look a little different. But peaks should be like very clearly observable if the addition of your analyte is making a difference. Um, but I do think that like CV of PVDF plus silicon oxide nanofibers. So I don't know if it's an option to try another thing. Let's see if you can, to keep the fiber structure. Yeah, I don't know if there's some special bonding to platinum that's happening. That's always a possibility. Other metals and materials that are like platinum are things like palladium and nickel. They have their own catalytic behavior, so to say, but the structure is a little bit different. So those are other things where if you're worried about the fibers, just bonding in a special orientation on platinum, you might try another metal. You may also try gold. Gold, other working electrode materials, or even glass or carbon. Anything that's not platinum, because platinum can realistically affect your results, should be indicative of whether there's some other interesting or useful chemistry that's happening. So, but yeah, I hope that is helpful. And you can ask, of course, for more clarification. I think following up on Pranav, I'm getting different anodic peak current in cyclic voltammetry for the same experiment under the same conditions. Why is it? So, Well, electrochemistry in general, I have found it's very difficult to always get reproducible results. This is a question of reproducibility and reproducible results. So one thing that I think is very important for you to do is before doing any interesting chemistry, make sure that you're able to get very reproducible results for a well characterized system with your cyclic voltammetry. And Pranav, let me just go back to make sure. I think you were talking about metal oxides, right? So in the beginning, you know, your preparation of the electrode, say like the working electrode, polishing, electrochemical cleaning, being able to reproduce the same or very similar cyclic voltammogram is very important. And taking a well characterized system, let's say ferrocyanide or ruthenium hexamine, being able to get reproducible cyclic voltammograms within a reasonable degree of error is one of the major goals that you should have when starting anything. And understanding your metal oxide, this is kind of part of understanding your metal oxide. Like, what system can you test your metal oxide in that might not be like the key high level research, but it teaches you something that's a stable, reproducible thing about your metal oxide, so that when you add your analyte, you know what things are coming from where. And that when you see a discrepancy, you can say, like, oh, I've been unable to reproduce the standard system. Something that has not only something that you do, but is something that other people, have published in the literature. As long as you're able to do that, you can. That's probably one of the best ways to troubleshoot why you're not able to get the same experimental results. But yeah, electrode preparation, stability, using the exact same settings, the cleanliness of the electrode, the cleanliness of your electrolyte, all those things can make a difference. And this is cyclic voltammetry. This isn't even like the hardest kind of like EIS is much more finicky when it comes to doing experiments. So hopefully that was helpful. I'm sorry that I can't. I hope that's helpful. I can. Hopefully if you need more clarification, or you can let me know. Okay. Rob, in Ragon plots, specific energy and specific power show reverse trend. What may be the science behind it? Garab, I've never heard of Ragon plot on the specific energy, so I'm sorry, because I will try to. I can look this up because I've never heard of one. I'm sure there is something interesting about it, but I'm sorry, I don't know the answer. And that's legit. It's just like there's some things in electrochemistry and science that I haven't heard of that I'm not gonna know the answer to. So I'm sorry, Garab. But yeah, if I use gold electrodes, then I can deposit nanofibers on it without making a slurry. Without making its slurry. I don't know. I don't know enough about your process, because I think you want to do exactly the same thing that you're doing on a platinum electrode as you would with a gold electrode. So preparing your nanofibers, however you prepare them, and then instead of putting it in platinum, put it on gold and see what happens. That's you're depositing nanofibers on it. So, okay. So when you deposit the nanofibers, they can make a slurry, which is not what you're looking for. You're looking for something else. So, I'm not so sure if it'll make a slurry or not. That's an experiment that you may need to do. I'm sure you want the nanofibers to kind of like stand up straight so that you're doing science on it, as opposed to them becoming kind of like a spaghetti slurry mixture. But I'm just thinking about similar electrode materials that might be able to just kind of help, and that might still have like this similar kind of chemistry to platinum that you might be able to use to do an experiment that otherwise you wouldn't, um, that you would normally use on platinum, but you can't because platinum's giving you some interference. That was kind of my thought, but I don't know whether how your thing's going to react with a gold electrode. Barry, great to see Barry again. Just wanted to thank you for another great live stream. I'm glad that you like it, Barry. Thank you. I have too many questions about HER and table slopes. It's too hot out and it's Friday. Yes. Yeah. Well, you can also, Barry, you can always ask us questions ahead of time. And then you can watch the live stream later if something is if something's on your mind, and we can try to answer it, especially when Neil will be back in next week, as he's on vacation this week. So that's me. Okay. All right. That looks like okay. Let's see. We got a new question. Himanshu. Hi, please explain to me again the diffusion process in batteries, and it is related to cyclic voltammetry. Thank you. So I remember Neil described this this process on the last live stream. He basically just had kind of a picture of this anode and cathode with a membrane in the middle, and then molecules of lithium ions diffused from one side to the next. But I think in general, you're curious about just diffusion in general, because I think diffusion is one of those topics that a lot of people have, in my opinion, a very big misunderstanding about. And perhaps in batteries, diffusion is a little bit different. But diffusion diffusion is this. Diffusion is the random motion of molecules. First and foremost, that's what it is. It's just molecules bouncing off of each other, going any with which way direction. And it's typically modeled as a quote random walk. I have a 50% chance of going, if you have a one-dimensional line and you can go left or right, there's a 50% chance that you'll go like left or you'll go right. And maybe even the chance that you'll have to stay in the same position. But that's diffusion. It is random. It is completely random. What ends up happening in batteries and in cyclic voltammetry experiments is that molecules that are near, and first and foremost, not first and foremost, but another thing is diffusion is a mode of mass transport, which means it's a way of getting molecules from point A to point B. They randomly move in some directions. You can move them through migration. You can move them through convection, forced motion of molecules. Those are all modes of mass transfer. So diffusion is a mode of mass transfer. It's the random motion of molecules, and it has to do with the size of the molecules, temperature, just kind of the conditions, the electrolyte that the molecules are moving through. If there are membranes in the way, it's how those molecules are moving. So all those things, that's what diffusion is, random motion. And your diffusion coefficient is indicative. It's a measurement of how quickly are those molecules moving. Is really like, what's the distance per unit time that these molecules traverse. So that's what it is. It's random motion. When you have an electrode and some kind of and it's at a potential where an electron transfer can happen, a molecule randomly moves to the electrode surface, whether it's a battery, anode, or cathode, gains or loses an electron, oxidation or reduction, and then it moves away. It diffuses away. Now, what tends to happen is that as all the molecules near the electrode surface, electron transfer is very, very fast, and ideally it's kinetically favorable. You'll get all of these electron transfers at the surface, and that's it. Once the thing's gotten an electron transfer, it doesn't need like a second one. So the only way more current is going to flow is if that molecule from, say, outside in the bulk diffuses its way towards the electrode. Then it can gain an electron or lose an electron and then diffuse away. Eventually, you start to build up a concentration gradient that the number of molecules, this is what's called the diffusion layer or the diffuse layer. Those molecules near the surface are almost all primarily the oxidized or reduced form, just because of random motion. when lithium ions move back and forth, and maybe Neil can correct me if I say this wrong, but my understanding of it very simply is like diffusion is just the random motion. Like lithium would move back and forth randomly from one end to the another of the battery, but there's a barrier in the way, and there's kind of this thermodynamic. Like, okay, well, you have all your, you know, when lithium moves, it quote intercalates into a lattice, right? So you're, I don't know, it's like a lithium metal battery. When you have lithium metal on one side, it's intercalated. So you have some kind of complex. Lithium atoms move in, they intercalate. They're kind of like they're in it. They're stuck in it. And then when the potential is switched or biased, the lithium moves out, and it just randomly moves. It's not like, oh, I want to use my, this guy wants to use his battery now. I need to go to the other side of the electrode. The lithium ions don't think that way. They just move randomly. It's like, oh, some constraints are different when I've activated or not activated, but it's just moving randomly. So, Himanshu, I hope this kind of helps a little bit. I kind of like I think a lot of people get diffusion wrong, and it's not to say that I have the best, most perfect explanation of diffusion, but diffusion is random motion. It is random motion, and molecules don't understand or think like, oh, you know, like think about a pressure differential. If you have a container of high pressure on one side and a container of low pressure, when you're learning general chemistry, we always say pressure moves from high to low when, say, that barrier is removed. The molecules don't think to themselves that it's like, oh, Alex said that pressure has to go from high to low. So because he said that, I need to go to that side because the barrier is gone. It's just moving randomly. It's just moving randomly. And it just so happens that high pressure is indicative of, say, more molecules or a higher temperature, which has more kinetic energy. So they just naturally start to move that direction. That's just what we observe. But it is diffusion. Anyway, that's my diffusion rant for today. I hope that you enjoyed that. The reason why I sometimes get I don't want to say like all up in arms about it is that some people will say things like diffusion causes or a concentration gradient causes diffusion. That's not true. Diffusion just happens. A concentration gradient is the result of electron transfer and diffusion. Like things don't like one thing doesn't cause diffusion. Diffusion's always happening. Okay, that's my rant for today. Also, for those of you listening, just kind of a quick reminder, but we're trying it out where if you are a tier 2 member and you want to join us on the live stream to share data, to ask questions, to ask in person and kind of like chat on our YouTube channel under posts, and maybe I can grab this, but under the posts for tier 2 members, you'll be able to see this. You'll see a link to our to the Restream where you can join the Restream studio, and you can join me and we can chat, and you can share some of your data, and we can talk about problems that you may have. So we're going to try this. We're trying it today. We're probably going to try this for future ones. So keep that in mind. If you're not a tier 2 member, we may extend this to tier 1 members. We're figuring it out, figuring out what's going on. Okay, let's continue. Looks like we have a good questions. Okay, so looks like I answered most questions. I'm going to now get to some questions that were asked earlier. This is from Tarek. Sorry it's taking me so long, Tarek, but you know how it goes. What's the difference between using floating and grounded mode on a potentiostat, and which setting is recommended for electrochemical techniques like EIS, CV and EIS? This is a good question. And this is something that I know the answer, but I would also say that my fundamental understanding of potentiostats between grounded and floating are is kind of still kind of weak, so to say. So when they say a potentiostat, and I would say almost any piece of electronic hardware, for that matter, um, you know, some electrical engineer said, "Oh, 2 volts needs to be applied to this part of the circuit to get it to work." Well, 2 volts with respect to what? Well, every piece of electronic gear has what's known as the DC common. DC common is known as the 0 point, the base level of that piece of electronics. So it applies 1 volt or -1 volt or something with respect to DC common, the voltage. Now, I don't have a power plug with me right now, but there are plugs that have, common like 3 ports, sort of say. They have multiple port um, power, and ground is connected to literally like the earth ground. So you have so the 3 prongs. Actually, let me just go to let's just go to this. Let me just kind of erase this here. But I think you've seen it. I'm just gonna draw it just kind of for speed. But like you always see something like this, and then there's like this kind of little thing here. It looks kind of like a little bit of a happy, unhappy face. And there's a voltage, right? There's like maybe 120 volts, depending on where you're from. And then this is ground. Ground. And literally, ground in some ways is a copper pole or a rod that is shoved into the earth, deep into the earth, ground. So so your power comes from here. There's a 120-volt difference from your power that goes into here. It then goes into some kind of adapter. It gets regulated because 120 volts will fry most electronics. So there's got to be, it also depends on the current that's being passed. But this is ground. Now, the DC common is just like the background base level. So one kind of good example of this is that if you actually took your laptop, for example, and if it was on battery power, that would be a floating laptop. It's not powered with respect to something. Its battery is disconnected from other things out there. Now, and so when it's grounded, it means it's like plugged in, and its reference point, not reference point, sort of say, but its reference point is with respect to the earth ground. I don't know if that's going to make a whole lot of sense to everybody, but hopefully it makes a little bit of sense. Now, the most important thing about these modes, like a potentiostat, can also be can it's usually plugged in. It has a ground cord connected to it, but its power can be disconnected, and that means it's floating. And floating is very important when it comes to connecting your potentiostat to other instruments. Because if you were to do, say, a spectroelectrochemistry or an electrochemistry experiment connected to a microscope, or something along those lines, there's commonly times where your potentiostat is integrated into another instrument. Well, you don't want your instrument to stop working because of an electronic configuration of another instrument connected to your potentiostat that's also connected to ground. Sometimes your potentiostat has to float for the experiment to work, which is useful. Now, here's the thing about grounding as it's determined for CV and EIS. When a potentiostat is grounded and it's connected to earth ground, it tends to have significantly less noise. And I'd say significant with perhaps a little bit of a caveat. If you're measuring microamps to milliamps of current, it probably won't matter very much if your potentiostat's grounded. But when you're measuring like low microamp to nanoamp current, grounding your potentiostat will actually minimize the noise. And one way I like to think about it is, if you've ever used, say, like a musical instrument, like anytime you hear like a bell chime or something like that, like this is probably not going to do anything, but I don't know if you can hear that, but this there's like a chime that's happening. Like I can make noise from it. It's a vibration that's forming. And it's wobbling. That's kind of your noise. That's your electronic noise. If that vibration is connected to a very heavy object, it dampens that noise, right? So a string is just like very light. It just vibrates a lot back and forth. It has to dissipate that energy just very slowly through the string, basically. But if it's connected to a really like heavy thing, like the moment you touch it, like if it's vibrating back and forth and then you touch it, it stops. You feel some of the vibration in your body, like a little bit. But now that energy is dissipated through your whole body. This is the same idea with grounding your potentiostat. Your potentiostat is kind of connected to a bigger body that can absorb, sort of say, those vibrations, and it won't manifest itself in the electrochemistry. So, the main thing, it's useful to have a potentiostat that can float because it can be used with multiple experiments and its grounding configuration can be adjusted. It's very helpful. But when you're just doing CV and EIS, especially in the low current range where there's lots of electronic noise, you probably want to ground your potentiostat. So that's kind of the answer to that question. That's from Tarek. We don't seem to have any other questions in the chat. If you have any questions, please write them into the chat. And of course, again, if you're a tier 2 member, you can join me and ask your questions live in person. So this is also related to the first question. So I know that some advanced potentiostat allow the working electrode to be grounded, reducing noise, especially ultra low current measurements. Is this a useful default setting, or are there any disadvantages to consider? So I can probably go through this quickly, but if it is grounded and it's not necessarily the working electrode. The working electrode is, quote, tied to ground, but not in the way of making it super advantageous or disadvantageous. It's mostly advantageous at reducing noise. The disadvantage has to do with using other instruments. So if you're using another instrument tied to it, that's going to cause a problem. But by default, Tarek, I would say it doesn't. It wouldn't have a disadvantage, and I almost recommend people to ground their potentiostat. The noise level looks so much better. Okay. Potentiostat software usually contains a technique to determine the open circuit potential of any electrode system. Can you explain how this technique works at a fundamental level? I will try my best to describe what I know about the open circuit potential technique, but I don't know if I can describe it. Oh, sorry. I don't know if I can describe it from like an electrical engineering standpoint. But really, the open circuit potential is what I would describe as a passive technique. This is analogous. Open circuit potential is analogous to taking a voltmeter and measuring the voltage between 2 points. That's what it is. It's almost exactly identical. In fact, it is identical to doing that. So it's what we describe as a, quote, passive technique, because we are passively allowing current to flow, or not current to flow, but we're not actively controlling it. Like when you're in a potentiostat doing cyclic voltammetry or bulk electrolysis, there's an active feedback loop that we are driving to force the potential to whatever we're doing. So that's an active electrochemical technique. But open circuit potential is passive. It's just allowing it's just measuring the potential passively. Now, what I understand very simply about it is there is, in order to make any kind of measurement, especially like to measure the potential, a tiny bit of current has to pass. A little tiny bit of current has to pass. And maybe this will be helpful if I do this. And this is just what I know. This is just what I know about these kinds of techniques. But basically, your OCP, open circuit potential, you have some kind of voltmeter. Okay. I'm going to make this like analog for now, right? So it's just this meter, and there's a dial, and it measures a voltage. And then I have one kind of probe on one side and some kind of probe on the other side, right? I don't know all the electronics of what's inside here, but one thing that I do know is that there is some kind of resistor. This makes a measurement by passing, there's some kind of very high impedance resistor. So this is super large. Maybe it's I'm just gonna make it up. I'm just gonna say it's 10 mega ohms. Something like that. 10 mega ohms. Okay. And what happens is a very, very, very tiny little current is allowed to pass through this 10 mega ohm resistor, and we can measure what the voltage is because we know Ohm's law. Um, I would say more accurately, there's some other circuitry that I don't know or don't fully understand. But there's a really, really high resistor. And as long as the resistance here, your electrochemical cell, the impedance of your cell in between these 2 points, as long as this is very small compared to this value, your measurements are going to be very accurate for the open circuit potential. Because basically you are forming, every time you connect your potentiostat to a system, it's becomes part of the potentiostat circuit. It's a weird thing to think about, but that's how it's working. So as long as the load of your open circuit potential system is not in this super high mega ohm regime, you are making accurate measurements. And hopefully this doesn't look like a milli. This is supposed to be something like mega. This is just big. You create these kind of circuits, these like voltage followers, voltage dividers, where you take a very small current that passes through. And then, I mean, to a degree, some of these voltmeters, the old analog voltmeters, it's just like a little dial. And when a little bit of current moves, like it just moves. It's just like, you probably can't see my head, but it's just a little dial that just kind of moves just a little bit. And that little current measurement helps us determine what the voltage is. I wish I knew a little bit more about it so I could help you or provide you with some more information or feedback, but hopefully that is helpful. That's part of it. Like how voltmeters work will tell you how open circuit potential works. But hopefully that gives you some information. All right. Also, just checking any chat questions. Looks like there are no chat questions coming in. I'm also going to check separately to see. Okay, also nothing. I'm also like I get stuff on Restream that helps me know what's going on, but sometimes I want to also check elsewhere. There's one other question I have that was asked by Tarek that I can at least answer. He asked another question that I don't know very much about, which is about kind of alternating current cyclic voltammetry, which is a technique that I have never done before or don't know. So his last question is, for visualization, could you draw an electrical equivalent circuit showing the position of the working reference and counter electrode? Yeah, I think so. I think I could do that. So let me just make sure I've got have this back up. Okay, so lasso this, delete that. All right. So this is how I think about it. And I'm literally thinking about like glassy carbon. Actually, let me type this in. So glassy carbon disc, working electrode, platinum wire, counter electrode, and then silver chloride reference electrode. And this is what I understand as best as I can about everything from an equivalent circuit perspective of these electrodes. So if I have, let's see, so, no, the thickness is gone. If I have working electrode, WE, here, and I'm in some kind of electrolyte solution, I have a Randall circuit, charge transfer resistance, double layer capacitance. There's some kind of solution resistance, Ru, that exists between the reference electrode. So Re is the reference point. This is where it senses. The reference electrode has also has what I would describe as a frit resistance. So this is resistance associated with a frit. And then Neil and I discussed this, but there is some kind of glass capacitance. Glass capacitance. There is some what we describe as compensated solution resistance between the reference and the counter electrode. But the counter electrode also has, it has an electrical double layer. It's a metal, like platinum, and it has a charge transfer resistance for Faradaic processes. So counter is here. Call that CTR, counter electrode. Actually, CTR. Maybe just counter. CE is good because I used RE for the other ones. So this is CE. Because whatever happens on the working electrode, like a metal surface, also is on the counter electrode. But we typically don't measure it, so it doesn't matter. The reference point where it senses is here, but of course the reference electrode. There may be some other things, like you may have circuit resistance here, maybe here. This is all circuit resistance, but this is the electrical equivalent circuit for a at least what I think to be the equivalent electrical circuit of the working reference and counter electrode. Especially, so it's funny. It's just like they all have some kind of resistances and random stuff associated with them. Okay. All right. I hope that was helpful. And I don't know the answer to Tarek, to your other question. I may have to ask Neil when he gets back. Okay. So with that said, doesn't look like there are any other questions. I'll stick around, just giving people some time and an opportunity to ask any further questions. Type them in the chat. Just a couple of heads up. We should have another Ask Us Anything About Electrochemistry live stream next week. I will be traveling, but I will be in a place where I will probably live stream from I'll actually be at the Pine Research headquarters, technically Pine Instrument Company headquarters. So I'll be able to hopefully live stream there, but I'll probably be there as a guest. I won't have this wonderful, wonderful office, but I'll be traveling that week. Neil will be back. He will also help with, so we won't be in the same room, probably doing the live stream. Again, if you are a member of our YouTube channel, you can come on in and ask us questions. If you tried to join and you ran into problems, please let me know in the chat or something like that. And yeah, we hopefully look forward to seeing you next time. Again, if you're catching this live stream later, not live, I will have timestamps in the description below in this video once it's uploaded, probably within a few days. You'll be able to watch it. Okay. So with that said, thank you all for joining us, or joining me for this Ask Us Anything About Electrochemistry live stream. It's always great seeing everybody and hearing from you as I just check you guys on the chat. And I hope you're doing well. Take care.